102 will get this. Okay.
Okay.
Right. But so let me just repeat your first question. So your first one was, why was it proportional? And as you said, it's because of constant friction.
Yes,
Yeah.
correct.
Okay, perfect.
Okay, and the next one, number 2, is describe and interpret the graph of the distance, the roll move versus the diverse full distance. So I see the description is a straight line, correct?
Yeah, good.
And is directly proportional.
Yeah, yeah. That's a straight line that goes through the origin is called directly proportional. So that's what you're supposed to notice. Yeah.
Sorry, one more time. What did you say?
A line that goes to the origin, or at least close, because we don't measure things perfect. Is called proportional.
Okay, so in the next one is describe and interpret the graph of the distance, the roll move versus the mass added to the driver. So like one more time, I quote you, is a straight line,
right?
And is directly proportional, because if you double the mass, you double the distance, correct?
Correct.
And if you
correct.
triple the mass, you triple the distance.
Right.
That's what you said.
Yeah. Yeah. Okay. Good. I'm glad you listened to me. Yeah, that's exactly right.
So this one summarize how mass and height affect potential energy. That one I don't have anything to say.
Oh, let me just double check. Could you read that one again? Is that because it's the two together, right? How does mass and height?
No, yeah. Summarize how mass and height affect potential energy.
Yeah, that question's kind of repetitive. Okay, let me go back 2 questions. You said that the energy was proportional to height.
Correct.
Then you said it was proportional to mass. So all they want you to say on that last one is that energy is proportional to both height and mass.
Okay, so that's gonna be all. So I think that's it.
Right.
I feel the this page. I already did this. I did the graphs. So
they look good. Yeah.
Yeah, and then the graphs are. I think they look good.
Yeah.
Like you expected, and that's pretty much it. Yeah, that's pretty much it. And then I just have to keep working in the homework for this week. And then, something else. I want to make clear that I already got a biology degree, a biomedical degree, I said, and I can't believe it that I already have a degree and I've been repeating like a parrot that that the kinetic energies is energy. I mean, is energy in motion, correct? No, it's what? Can you say that? It's kinetic energy. Kinetic energy is motion in distance. Well, how do you say that? You say that. You explained that in the last class. Kinetic energy.
Kinetic energy is force time.
No, but you said that it was in the lesson that you were saying that explaining that how is motion, how it goes. It goes. I think I have to check on my notes.
Yeah. Yeah, I'm not sure what you're asking. Kinetic energy is one of the energies, right? And has to do with motion.
So say one more time. What did you say?
It has to do with motion. So, more mass or more speed results in more kinetic energy.
Yeah, and then the thing is that I have in my notes. I think I don't recall exactly what I was going to say, but the thing is that I never understood that question until you explained that.
Oh, well,
I just can't believe it, because I already know that potential energy is the potential energy. Like if something is really high and is heavy and that fell, is going to destroy a lot of things. If it is higher, it's going to destroy more. So I know that about potential energy. But the other, the kinetic energy, that is, I think is, I just forgot what you said. And usually they say that on the t-shirt, but I never understood until you explained that.
Oh, good. In fact, I think you explained it really well by putting your hand up in the air. But you did potential energy. I would go sideways with kinetic and say, you could do more damage if you had more mass. You could do more damage if you went faster. So it has to do with mass and speed, whereas potential energy has to do with mass and height. Mm-hmm.
Okay, yeah. So so I just want to mention that, and maybe I'll check on my notes again, because I have that in my head. I know that as a fact, because I've been repeating that as a parrot all the time and never understood what it meant until you explained. I think it's something about motion, like how it goes rolling. Or you were saying about the ability, like the kinetic energy. I think you said that is you have the ability to do something, but that doesn't mean you don't do it.
Right.
Something like that. I think I got lost myself.
Right. It sounds like you're saying there is a small subtlety between work and energy, because energy is just the ability to do it. Work is actually getting it done. So, like for me, I have the ability to lose weight. I just never do it.
Okay. Okay, that's a good explanation. But anyway, I just want to thank you for that, because I never understood, and now I just feel like I know what it means, because at the beginning I never understood that. Oh, actually, I found that. I found the notes, and it said energy, the ability to work, and then work, and then it said sorry, workforce discounts. That's what it said. But then how do you define kinetic energy in your own words?
What?
Energy in
I
motion.
call it.
Energy in motion.
Yes.
That's correct.
That's correct.
Yeah, that's it. Energy. Yeah, that's it. So I never understood that word until you said, why is energy in motion, all that stuff. But it's because it's rolling, it's distance, and all that stuff involved in it. Anyway, thank you so much. Okay.
My pleasure.
I'll let you be, okay?
Okay.
Okay.
Bye. All right, now I'm going to look over here on the chat room for you guys. Anybody throw me up a question? Well, no one yet. I guess I should point out, if there's anybody here from 121, I guess you guys have the preference right now. And that was actually some good 102 questions. I'll write those down. Let's see. But make that my little notes. And then, as I got to say, I have these 102 questions I got by email, but I'll probably do those outside of this time frame. I think that'll work better, unless I was going to say, unless anybody hears from 102, but I don't see anybody here from 102. Okay. All right, Hunter, you're going to shoot me one here from chapter 20, number 60. That'll be good. Let me write it down here. Chapter 20, number 60. Let me put a time here. What is this? 12:41. Okay, nice. All right, let me switch over here to our homework. And right before the break, let's see, we were in chapter 21. So this will go back to number, yes, I read this one. This one caught my attention. This one looked hard because of the differential equation. So good. Let's work on that. Let me turn on my phone. I can make a connection here. Okay, let me share my camera phone with you. Yeah, this is, I think any of them that uses differential equations and rates is always a challenge. But this one's extra challenging because of some other things here you'll see here. All right, so number 60 says that we have a pond of water at 0 degrees that's covered with a layer of ice. So maybe I'll kind of just start by seeing if I can kind of figure out. So here's the pond, if you will. Maybe we've got water up to this level. So underneath is a liquid, and it's cold liquid, so it's got down to 0 degrees, which, as you know, when the liquid gets down to 0 degrees, it starts to harden and starts to freeze. And of course, it's in contact at the surface with the colder air temperature. And so that goes on to read that the air temperature above it is at negative 10 degrees Celsius. So there is this constant flow of heat out of the water that's in the pond. And as it loses it, the layer of ice gets thicker and thicker and thicker and thicker. And if long enough, get thick enough to stand on and skate on, and actually gets thick enough you can drive a car on it. But the point is that the water down here is all probably around near 0 degrees Celsius. And so there's a constant temperature difference. Anyways, and so the heat has to conduct through this layer of ice, which isn't easy for it to do. Plus, the layer gets thicker and thicker with time, making it harder and harder. So the thicker the ice gets, it actually kind of inhibits itself from getting even colder and colder. You might say, in a kind of a weird way, it's making its own blanket. It's keeping a boundary, and that boundary is getting thicker and thicker between you and that or it and that cold environment out there. And it's still conducting, so it's still going to get thicker and thicker. So as long as it's less than 0 degrees up above it, it's still going to get thicker and thicker. But its rate of growing would change, and that's where this differential equation comes in here. All right, so a pond at 0 degrees Celsius is covered with a layer of ice, and they're saying here it is 4 centimeters thick. If the air temperature stays at a constant negative 10 degrees, what time interval is required for the ice thickness to increase to 8? All right, so the equation they're suggesting is the equation for thermal conductivity, or at least I should say thermal conductivity in one dimension. And let me write it here and then talk about what these pieces mean. But this was derived in the book and in the lecture by saying that if you just had a metal rod here, and at one side you have let's say a high temperature, and the other side you have a low temperature, and some length L, and then some cross-sectional area, the heat would flow through here, dq dt. And that's this part. So this is the rate at which energy is flowing. And that's, I guess, what we mean by reading the math. When I say read the math, is this dq dt. This is the rate at which energy has to move through the rod. And you can see here that there are 3, maybe 4, depending on how you want to look at it, factors. But the K value is the material itself. How well does heat move through that material? And so silver is the best of the materials. It's the best of the metals. I think diamond might beat it. A is the cross-sectional area, so it kind of makes sense that the bigger this rod is, the the more space it has for the heat to flow. So it's not just the material, but then, you know, how much room does it have to actually flow? And then this is what you might call the temperature gradient. This is how does the temperature change with length? You might say this is the push. You know, if there's only a 1 degree difference, it's not much of a flow of energy. Whereas if something is 100 degrees difference, then there's a much bigger flow of energy. So, and of course, it's the temperature difference per length. So, you know, 100 degrees that is spread out over hundreds of miles doesn't conduct very fast. Whereas 100 degrees over a separation of a millimeter flows really quick. And so you can think of this as one term or two terms. It's got temperature and length, but it's a gradient, I like to say. So I think of it as one term. So these 3/4 items that determine how quickly the material flows. Now, I think all of the problems on this page are related to thermal conductivity in some way. In fact, that's the lab you're going to do next week. Is we're going to actually measure the thermal conductivity of 5 different materials, and I'll be a lab partner again, and we'll kind of set up a little experiment and measure how quickly we can melt ice. We make one side real hot with boiling water, so that's 100 degrees, and we make the other side cold with a block of ice, so we know the temperature difference is 100 degrees, and then we measure the thickness of our different materials. Sadly, they're not all the same thickness, but maybe that just adds to the lab, so we got to measure the thickness of each of them. Anyways, let me not go down the road of the lab too much here, but you'll see that one and hopefully help you with this equation. But here's what this is trying to say here, is that this temperature then gradient would be this. It would be minus the K times the area. And then the gradient would be the temperature difference between them, okay, which is 10 degrees. So 10 degrees Celsius spread over, and I'm going to call this a length X. And so maybe the hardest part of this problem is to really say that a dT dx, if you have the same material, would be the separation in the temperature over the separation in distance. And this is, I guess, in math terms, where you would say this is the slope and this is the derivative. The slope is the tangent line. So if you have something on a graph, I'll just go back to your math class, that, you know, here's the x-axis, here's the y-axis, and it's a constant slope, then the tangent and the slope are the same. And that's what I'm going to say here, that it is spread evenly out. Now, here's where it gets complicated. The x changes with time. I get that. But at one moment in time, this x is a set value. It starts at 4 centimeters and eventually gets thicker and thicker and thicker up to 8 centimeters. So I'm going to say that this x represents the thickness of the ice.
Mm-hmm. Does it, because we're looking at it just like two-dimensionally, does the surface area of the ice exposed on top and below matter, or like we actually...
Yes, it does matter. Although, well, well, it's both yes and no. Let me just leave it there for a moment, and I think I can answer your question better when I start working with the other side of the equation here. All right.
Sounds good.
So, all right. So I'm going to leave this alone, and in fact, I'm just going to do absolute value. So let me just go ahead and just drop the negative sign away, and I'll just recopy the right-hand side. So we've got 10 degrees Celsius over the thickness X. But I think what you're going to see here, and let's talk about it, is you're going to see an area on the other side, which is going to cancel off. So in one sense, you're going to say mathematically it doesn't matter. However, if we read the math, it kind of does matter. I'll explain, but let me just work with this. And so I'm going to go dt. I'll just do the derivative, but the q then is really then showing up at the rate at which the water is freezing. Okay, so what I guess I'm trying to say here in this chapter 20, what we call the latent heat, let me put it over here on my page 1, is Q is equal to MLF. Okay, in other words, if you already have water at 0 degrees, we're not dealing with the MC delta T. What we're doing is just freezing it. And so right here in the bottom layer of the ice underwater, what's going to happen is the ice is going to go from 0 degrees liquid to 0 degrees solid. Okay, so what I'm trying to say in this is this Q, which is the heat that goes from the pond through the ice out into the atmosphere, shows up as a thickening of the ice down below. So I'm going to write this as MLF. That's the heat that leaves. The heat that leaves then makes the liquid into a solid. There is no change in temperature. Okay. Now, the reason that's helpful is because the latent heat of fusion is a constant. And so now we've got this dm dt. And reading the math, this dm dt is the rate at which the mass is forming as ice. Now, we are not asked exactly for the formation, the rate at which it's forming, but we are asked to when it will get thicker. So let me keep reading here. It says, because they give us kind of a helpful hint that I might have already done, but it says, note that the increment of energy dq extracted from the water through the thickness x of the ice is an amount required to freeze the ice of thickness dx. That is, and then their helpful hint. Now, I've only done half of it. So let me keep going with their helpful hint. I've done the half that said that the Q is M times LF. But let me then do the second half. The second half is to say M, and this goes back to the chapter 14 again that we kind of did before the break. Maybe I'll put it up here, but density is mass over volume. And volume of the ice then would be mass over its area times its thickness. And if we rearrange that, then we could say the mass of the ice is the density of the ice times the area of the ice times the thickness of the ice. And that's what I need to put in for this equation for the mass of the formation of the ice, a rho, an A, and an X. Now, again, thinking of this as ice, the density and the surface area of the pond doesn't change. So I'm going to pull out the density and the surface area, and I have now what's going to be useful, a dx dt. This is the rate then at which the thickness of the ice is changing. And so you can see that this this left-hand side of the equation ties all the way back to dq dt, right? dq dt, this is the rate at which energy is being lost. And the rate at which it's being lost has to do with the rate of the mass that's being formed into ice, which has to do with the thickness that is being formed. So there was a couple steps going from the dq dt to a dx dt. That's one of, I think, the two hard steps on it. Now, let me write down the right-hand side of the equation, and this is your kind of your question, Hunter. Does the area of the pond matter? No, not really, because they show up on both sides of the equation. Or I would put it this way. Yes, the area does matter in the sense that more area conducts more heat. However, that faster area, which would then freeze more volume of ice, is spread out over that same surface area, so it doesn't change the rate of the thickness of the ice.
Okay, I get what you mean there.
Yeah, so the thickness of the ice, the growth and thickness has really nothing to do with the surface area, but the rate at which heat is leaving and the rate at which the volume of ice is being formed does. All right, so fortunately, they do cancel off because the problem doesn't tell us anything about the area of this pond. And we would be stuck, otherwise. All right, now, the other hard thing about this is we have a differential equation. So let me just write what I have. I have LF, and so this is the latent heat of fusion of ice. I have rho, that's the density of the ice. I have the forgot the whole derivative. I have the dx dt, and so this is the rate at which the ice is being formed. Then I have it equal to a k, a 10 over an x. Now, I think the second challenging thing for you guys will be now the math, solve this, because differential equations tend to be, I think, the highest level of mathematics we do in this course. And I should point out that the place where you guys learn differential equations, which is Math 220, is not a prerequisite for this course. Fortunately, though, there are some differential equations that are really easy. They're separable. And you've been doing that since Math 160. And so in Physics 121, as well as 122, as well as right now, 123, we come across separable differential equations. And so you are expected to solve them. And what does that mean? Well, separable are the easiest differential equations to solve for. They're called separable because if you have an equation that has two variables, which in this one you can see that I have the variable x, and I actually have the x and the derivative of x, and the other variable is t. And if you can rearrange this equation so that all the x's are on one side and all the t's are on the other, then it's separable. Now, the advantage of that is then you just integrate it and you have just only x's on one side. So you're doing an integral with respect to x. And then you have t's on the other side. So you're just doing an integral. So that's why this is first presented to you in Math 160, because you've already learned integrals back in Math 150. So, hey, these type of equations that are separable are the easy ones. And fortunately, this is one of those. So let me continue on. And say, all right, page 2. Let me put, and it doesn't matter where my constants go, so I just like to put them all together. So I'm going to put the K and the 10 underneath the latent heat of fusion and the density. All my constants are together. And I'm going to put an equal. And then I got to decide which side I want to move things. And it looks like I already have a dx on the left-hand side, And then moving the X to the left-hand side would probably be the way to go. All right, so I'm going to move X's to the left-hand side. And that means that everything with the T goes to the right-hand side. And again, maybe just to make it sound easy, it is a differential equation, but it's like, hey, that's the only thing that has a T. It's just a dt. So it's kind of a boring step, but nonetheless, you can see that I've got everything with X's on the left and everything with the T's on the right. And again, the reason that is useful is then we can just do a big integral of both sides. And on the left-hand side, we would say, okay, start at some initial thickness and go to some final thickness. And on the right-hand side, we would say start at some initial time and go to a final time. Now, for the left-hand side, they make it very clear that we are starting the ice of a thickness of, and I believe it was 4 centimeters. And we are to let the ice get thicker and thicker until it gets to 8. So that would be the limits of my integration. So from 0.04 to 0.08. Now, the other side of the equation would be some starting moment in time. And we can pick that whatever we want. So we should probably say, let's call that time equals to 0. So time is equal to 0 is when we have our 4 centimeters of ice. So the pond is got 4 centimeters thick of ice. And then let's call the final time the unknown in the problem. That's what we're trying to find, right? We're trying to find when does the ice get 8 centimeters thick. So that's really what we want to find. And since the right-hand side is an easier integral, I'm going to do that. So the integral of dt is t evaluated from 0 to t, which means I just get a t. So there it is. That's what I'm looking for, the t. You know, when will it get 8 centimeters thick? Okay, now the other side is fortunately an easy integral. This stuff's all a constant. So I'm just going to put L sub f and the density and the k and the 10 all out in front of the integral. And then I just have an integral of x dx, which would be x squared over 2 evaluated from 0.04 to 0.08. And now I can start putting things in. And maybe to give myself a little bit of space, I'm going to put the t a little further to my right and start to put things in, starting with the latent heat of fusion. I probably should look it up, but I'm remembering that at 335 joules per gram. And I think I left the textbook open from earlier. Yes. And latent heat. Oh, that's specific heat. Let's go to I think it's table 2, a little further. There it is, table 2. Let me make it a little bigger so I can read it here. Water, there we go. Latent heat. Actually, it's 333. Oh, and they do per kilogram. So I guess I should too. So, well, my bad. I'm going to rewrite that. So they do 3.33 times 10 to the 5 joules per kilogram. Okay, so there's the latent heat of fusion. I also need to know the density of ice. And I'm going to try my go-to chapter 14 again. but as you know, I didn't have real good success. Densities of common substances. Ah, they do got ice here. Nice. Let me make it a little bigger so I can see it. But the ice is 0.917 times 10 to the 3. What are the units here? Kilogram per cubic meter. Okay. Now the K, you got to follow all the way back here. That's the thermal conductivity. So that would be in this chapter. So let me go back to chapter 20. Let's see, specific heats, latent heat. Well, I bet it's near the end. Thermal, here we go, table 3. 100%. It says the thermal conductivity of common substances. Here's ice. So ice has a value of 2, the table says. Wow. Now let me look at the units. The units are watts per meter for each degree Celsius. And then this 10 is 10 degrees Celsius. Now I probably need to put in my X's here. And I'm looking at my units going, okay, I better put this as meters, I think. Oh, and I did. That's good, because those were centimeters. I put them as meters. So this would be 0.08 squared, and that'd be meters squared over 2, minus 0.04 squared meters squared over 2. That's the time. All right, now I'm going to check my units here, and then I'll put in my numbers. But I hope this comes out to be seconds. Let's see. The degree Celsius would cancel off. That's good. Right here in the numerator, I see kilograms cancels with kilograms. That's good. Now this cubic meter with this square meter will almost cancel, but remember this over here is a compound fraction. So this meter is going to flip over and make cubic meters with those meters squared canceling with those. So that's good. Oh, and then this is excellent. This watt right here is a joule per second. And so that means the joule would cancel off and the per second would flip in the compound fraction and get units of seconds. So I just wanted to make sure I didn't mess up my units here. And it looks like they came out in seconds, so good. So now I can grab my calculator and say, okay, let's do this. 0.08 squared divided by 2. Subtract 0.04 squared divided by 2. Well, that'd be that number. Multiplied by 0.917 times 10 to the 3. Multiplied by 3.33 times 10 to the 5. Divided by 2. And divided by 10. Am I missing any numbers? It looks good. And so it looks like about 36,643 seconds. Now, if I divide that by 60, it's going to be that many minutes. Divide that by 60, and it'll be that many hours. So it looks like we need about 10.2 hours for the ice to gain thickness. Oh, and I kind of froze there, huh?
I mean,
Stop
luckily we were already at the end of the problem, you know.
that. Yeah, luckily here, but let me just redo, let it kind of do its thing and redo its connection while I kind of give a little nod here to the solution manual. Let's see. Last time we were in chapter 21, so I need to go back to chapter 20 and scroll to number 60 here. Yeah, and they got 10.2 hours also. Nice. So
Cool. Thank you. Yeah, I had a problem with just interpreting the first part and the diffie Q and stuff. So
yeah, I think all the ones on this page really can be a bit challenging, and I think it's because the equations kind of have a derivative in them, and you got to kind of have to go, okay, what is being held constant? What is changing? And so reading the derivatives into the math is crucial to know what to put where. All right, so let's see. Did anybody else throw something into the chat room? Whoops. Okay, I lost my chat there. Okay. Nope. Nothing else yet. So I don't know. Anybody else wants to grab anything or has a thought?
if we don't have anything, I wouldn't mind going over 61. That's a
Okay.
yeah.
Yeah, you guys are kind of the speakers for the whole class because a lot of them are just hanging out to see the videos. So they're hoping you ask some good ones. Okay, now you said 61, same chapter?
Yeah, chapter 20.
All right, let me write that down here. So chapter 20, number 61, and it looks like we'll start this one at about 114. Okay, so chapter 20, number 61, and it must be just the next one. And I bet again, it's kind of that same thing of we've got the rate at which heat's being transferred. And these are all challenging ones here. Okay.
Are these like later ones, the ones we could expect lengthwise to be on the test, or are these like is 60 or 61 like what we would see on the test?
Yeah, I think I haven't done 61 here yet, but 61, as I scan the picture and read the numbers, I think this is a pretty straightforward one. I don't think this was going to be to the same level. So 60 is a hard one, but it's so it would, if it was on the test, it would be like my number 5 one. There wouldn't be two of them this hard.
Okay, I see.
But I don't think 61, and I don't want to speak too early, but I don't think 61 is going to elevate to a real hard one.
Okay.
Tough to know here. Let me just read it here, and I'll try it. It says the average thermal conductivities of the walls. See, and then that's one of the things that kind of clued me off. I go, look, this just looks like a rectangular box, and everything's the same thickness, everything's the same material, or not. It's not really the same material, but they averaged it all together, and so they did kind of. How would you describe that? When things get real complicated, you just kind of average it over. You just say, well, that's kind of where the science turns into engineering. You're like, well, I don't know all the details, but what I could do is just kind of do an average effect. And the house has windows. Maybe part of the house has a brick on it, or rock. A lot of houses have the lower half are rock, and that makes the walls a little thicker, and therefore the conductivity is different. Most of your houses put a different insulation in the ceiling than the walls. Number one, there's just more space, but number two, hot air rises. Anyway, so to just average it over that completely ignores the complexity of it, which makes me feel this is going to be a little more straightforward problem. Well, that's why I said that at the beginning, but I'm going to read it again. It says the average thermal conductivity of the walls, including the windows and the roof, is dictated in figure 61 and is given by this value. So I'm just going to put a K value of 0.480 watts per meter per each degree Celsius. And their average thickness, so I'll just maybe say L, is 21 centimeters. So again, we know windows are thinner than walls, and we know walls are thinner than ceilings when you add insulation. And so again, I really think they, are very much overly simplifying the reality of it, and therefore it's going to make just kind of a straightforward problem. Now, the house is kept warm with natural gas, having a heat of combustion, that is the energy provided per cubic meter, of 9,300 kilocalories per cubic meter. How many cubic meters of gas must be burned each day to maintain an inside temperature of 25 degrees Celsius if the outside temperature is 0 degrees Celsius? I don't know if you guys have been watching the news, but this sounds like a Texas problem right now. Like, okay, you got to burn a lot of natural gas to stay warm, and anyways, or to make your electricity. And
Texas is one weakness is snow, I guess.
Yeah. Well, the interesting, they're having the same problems that we would have if it got that cold here. I mean, I was just thinking about my house. I said all my pipes would burst because none of them have insulation for the cold weather, and all my natural gas lines would freeze. I don't know about the gas company themselves as they deliver them. They seem to mostly be underground, so I'm thinking maybe they would be okay. And that's kind of where they're suffering. They had a lot of natural gas lines above ground that then generated their electricity, and now they just don't work. So, the electricity plants went down. So, yeah, terrible. But we're not planning for it, so hopefully it won't happen to us. But that they did the same thing. They didn't plan for it, and it happened to them, and it's tragic over there. Yeah. And I heard a date. I heard it has not been this cold in Texas since something like the mid 1800s. So kind of, you kind of wonder if the political fallout will be interesting. You kind of wonder if if you should have planned for it, or if it was just a fluke of nature. I don't know. Anyways, so oh yeah, and if there's a political fallout, I wonder what will happen here. I mean, well, for anybody's individual house, you can do whatever you want. So I don't know. Maybe I should get in my attic and put insulation lines on all my water lines and.
I'm really hoping it doesn't get that cold here, though.
Yeah.
That's I believe we already did that in our house because when I the winter I was born,
Uh-huh.
a lot of the pipes in Lompoc burst just because it's in a valley, so it keeps the cold air in somehow. So I think
Lompoc can get surprisingly cold.
Huh?
Yeah, Lompoc can get cold. I mean, not like mammoth cold, but.
But I mean, in winter it can get down to it's easily been in the 20s before.
Okay.
So like I think a lot of the houses in Lompoc like already put insulation around the pipes and stuff because we had a lot of the town had their pipes break like
Mhm.
22 years ago. So
Yeah, yeah. Well, yeah, it only takes one time and then you decide, oh, we better do it. It's a mess.
Yeah.
But
I wonder if that's going to be a recurring thing or what's up with that too. Cause it's, yeah, just the storm. I mean,
oh, yeah, well, I do think it's going to be recurring only because it's that polar vortex, which is part of the weakening of the Arctic air and the climate changes. But yeah, I think they just need a plan for the future and say, this could happen once every 20 years. Even though
that's
even though
rough.
it's even though it's been something like 170 years, they just better plan for it more often because polar vortex is gonna keep dropping, and the East Coast is gonna see this massive cold. I think. Who knows? You never know what. Well,
Yeah.
and here on the West Coast, we'll see warmer temperatures. So there you go. Well, yeah.
Yeah, we've had like no winter at all, basically. So
Yeah. So, fortunately, Northern California is still getting quite a bit.
yeah.
Which, since we
Yeah.
bring so much water down from them, we can be okay.
I have a friend that lives in Mammoth, and she has been having like powder days every single day for the past like 2 weeks.
Oh, nice.
So,
Very
yeah.
nice.
They're getting a lot of snow up north.
Any idea how much snow?
It
I should look.
did like one of the days she was there, it did like 5 inches, 6 inches in one day.
Sure.
Like,
Well,
it was a
there's
lot
been
of snow.
yeah. Well, there's been times in Mammoth where you'll go up in midwinter, and I've skied above the top of the trees. I mean, there's no trees because literally there is over 35 feet worth of snow, and every tree is under snow, and you're skiing down on just a bald mountain. It's amazing. Crazy when it gets that much snow. But Mammoth is an interesting spot. They get more snow than anywhere else because they're at San Joaquin River Valley. All the moisture from the Pacific can go right through there, and they get blasted with more moisture than any place else in the Sierras. So they got the high elevation and a natural pathway for the moisture to get there.
I know it's really weird if you think about it, because it's like it's one of the places that has snow almost all year long, yet driving to it can be some of the hottest places there are.
And no snow until you get there. I mean, you're
Yeah.
driving through the Owens Valley, you're at 6,000 feet, you're in a kind of a desert ravine, and beautiful mountains, and no snow. You pull off. It's on the edge of an old volcanic, what do they call those? Candoras or Candelas? But it's on the edge of an ancient supervolcano, and so it's in a huge valley, and you just turn off the road, and all of a sudden you're there, and like, wow, look at all this snow. Where'd this come from? And you don't have to drive through it. Yeah, Mammoth is perfect. And what's really interesting is when the guy who built Mammoth, last name, very interesting history, like a Mick Corey or Mick Coral or something. He wanted to build a ski lift there, and he brought in some professional ski lifts from Switzerland, and they told him it would be impossible. You can't build it. There's too much snow in this place. We're leaving. And so they just bailed on him, and he goes, no, this is the way to do it. And so he started building these lifts on his own. At first it was rope tows, and then it was lifts, and then I don't think he planned for this. The funny part of the story is it was right after World War II. He put all this money into it, and then he wanted all these people to come up and go skiing, but the snow was so thick that none of the roads were open. And so in his creative genius, he bought surplus, for lack of a better word, I'll call it tractor equipment, but it's not a tractor. The U.S. Army had a lot of these snowcats. You know, it looks like a big tractor that can go over snow. They used them in places like Alaska and the Aleutian Islands and northern Russia. Anyways, they were surplus. So he bought these snowcats at a real cheap price. And what he would do then is he would drive the snowcat just the 10 miles or so to where the cars could get. And then the people would get on their skis and he would just toss them like a tow rope, like a boat and a tow rope. And then they would grab it and that'd be half the fun, just getting to the lift. So they'd get there and he would drive the snowcat back to the lift and he'd just do that all day. And that just became like this hit, you know?
So cool.
So yeah. Well, when you're in business, and in this case, doing something new, both your engineering skills and your business skills got to be creative and flexible.
And that definitely played off too.
Yeah. And of course, look at Mammoth today, right? Yeah, crazy. Okay, well, back to this problem. All right, so this is the average thermal conductivity. This is the average thickness. The house is kept warm by burning natural gas. How many cubic meters of gas must be burned each day to maintain an inside temperature of 25 degrees if the outside temperature is 0? Disregard the radiation and the energy loss to the ground. All right, so I'm going to start this with the same equation we did on the last one. The dq dt equals minus k a and then dt dx. And maybe I'll just pay little attention to direction and just do absolute value so I can drop off the negative sign. And this stuff really they gave me. You can see that the thermal conductivity on average is 0.480 watts per meter per each degree. Maybe the hardest part of this is the area. I'm going to leave that one alone because this building, let's talk about its geometry and how much area it has to lose heat in just a second. But we can then do like in the last problem and say, let's just say the material is uniformly distributed. It's not, we have averages. But then on average, we can say the average slope is equal to the average tangent. So the temperature difference between the inside and the outside of the house is on average 25 degrees. I believe, let's see, the inside we wanted 25 degrees and the outside is a cold 0 degrees. And the thickness, as they said, is an average of 21 centimeters, which I'm going to write as 0.21 meters. Okay, actually, before I put equals, let's talk about this area then. And so the total area is, and so I'm looking at this house. Okay. Maybe I'll try to draw a picture of that house. So there is a wall that maybe I will call it the side. Then there is a front of the house. Then the roof line goes up and comes back down. So there's like a little triangular piece that is on the front side of the house. Then there is what I call the front of the roof. And maybe the back of the roof. And can't really see in the picture, but over here there'd be the back of the house. And then there would be the back side. And the back side would look a little bit like the front side, where it has a rectangle and a triangle. So the heat would get lost in all of those surfaces. And of course, we're just going to pretend that that's all averaged out by this number that they gave us as the average thermal conductivity. So now it becomes this question about area. So let me do maybe the front first right here. So here's the front of the house. If I look at the dimensions, it looks like it's 10 by 5 meters. So 10 by 5 is 50 square meters. There's the front of the house. And by symmetry, I'm going to just multiply by 2 for the back of the house. Maybe I'll also do what I call the side front together with the side back. So the side front looks like it's 8 meters back and still 5 meters up. So 8 times 5 is 40. So that's 40 square meters. And then let me again double it, because not only there would be this side front, but then there is the side back. All right, so I've done these 4 surfaces. I should probably do maybe then this triangle. And it looks like they put 37 degrees there. Maybe I'll come to the top edge here and draw kind of a triangle that has an angle of 37 degrees and would have a base of 8 meters. I can get its height then by doing
I think you
something.
froze up.
Oh, hey, all right. Let me feel the temperature of my phone. That was my theory from last time, that we really lost it when it got overly hot.
Mhm.
But it doesn't feel overly hot. I'm not getting a warning sign. But don't have a explanation. All right, well, let me get this reconnecting here. And I was trying to do when it was froze here was trying to draw this triangle up here and say that the sine of 37 degrees, I kind of split this in half, would be this height that I'm looking for. I'll call it h, divided by, say, oh, not sine. Let's do tangent. Tangent. So tangent would be opposite over adjacent. So tangent of 37 degrees would be h over this half of it. So that's a 4. And so that's going to give me a height of, and am I in degrees? I am, good. So let's go tangent of 37 degrees and multiply by 4. So about 3 meters, 3.01 meters. Okay, so now I'll come back here. I'm trying to get the area. So the area of this triangle on the front side would be 1/2 times its base of 8 times its height of 3.01 That 2 would be in square meters, and I can also put times 2 because there'd be a triangle on the front side and then the back side. All right, so let's see. I should have 6 surfaces so far. 1, 2, 3, 4, 5, 6. Yeah. Now, the last 2 would be the roof line here. And the roof line in this picture, the length of the house is the 8 meters. So we know the length here. But now I need this slope. I'm going to come back to this triangle here. And it doesn't matter which side. But to get this hypotenuse, I could do sine, or I could just do Pythagorean's theorem. Maybe I'll just do Pythagorean's theorem because this would be a 4. So I'll go 4 squared. I'll add this height, 3.01 squared. Oh, that's a 3, 4, 5 right triangle. Okay, so that's 5. Yeah, so sure enough, this is 5 meters. So we've got 5 meters along the roof line. Okay, so anyways, this part of the roof right here is 10 by 5. So that's 50. So I'll have 50 square meters. And then each side of that roof is times 2. So this is probably the big challenge of this problem was just going through the area. So let's put in some numbers here. Let's see. 50 times 2, that's just 100. 40 times 2 is 80. 8 times 3 is 24. And it looks like another 100. All right, so we're looking at about 304 square meters. All right, so now I can come back to before I got involved with all this geometry and say, all right, so the dq dt, at least the absolute value, so the rate at which heat energy is leaving this house would be 0.480 watt meter for each degree, a surface area of 304 square meters, a temperature gradient of 25 degrees Celsius spread out over 21 centimeters. So let's see, the square meters would cancel off degrees Celsius, and it looks like we'd be left with watts, right? Which is an energy per time, and that's exactly. So it's going to be so many joules per time. All right, so I already got the 304 in my calculator. Let me go 0.48. Let me go times 25. Let me divide it by the 21, and I get 17,371 watts, or joules per second. All right, now I'm not quite done. I think, though, that's kind of the main point of this particular section in this problem. They do ask how many cubic meters this would be. So this 17,371 joules per second must be burned in a day. I first would multiply by 60 seconds in a minute. Then I'd multiply that by 60 minutes in an hour. And then I'd multiply that by 24 hours in a day. Okay, so times 60 times 60 times 24. So this is 1.50 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 joules per day. So 1.5 billion joules a day is what's needed to keep this house warm. And I know when you say billion, everything sounds big here, but a joule is not much energy in terms of warming a house. So, but still. Okay, so now we are after how many cubic meters per day is this? So if we say that I have 1 cubic meter is equal to 300, and they say kilojoules, so I'm going to put 300,000 calories. I don't quite get what I want because the joules and the calories don't quite cancel, but I do get cubic meters per day, and that's what this is problems after. So I've got my joule calorie issue, but I know that there is 4.186 joules in 1 calorie. So that's another unit conversion calculation. So I suppose in one sense, kind of reminding you way back in chapter 1, if you can remember that long ago in Physics 121, chapter 1, where you're like, okay, how do we convert units? So to go from joules per second, which then became joules per day, and now joules cancels off here and there, calories cancel off here and there, and I'm going to be left with cubic meters per day. So maybe this is a little harder in the sense that there's some tricky unit conversion here, but in terms of the thermodynamics, this is just the rate at which heats flow and kind of a one-dimensional problem. We don't really do more than one dimension because, as I was saying, too much of a differential equation. That's what you will probably do in 122. I know, math 220. I know they try to teach you how to solve a lot of differential equations, and one of them is the heat equation. So they give the multi-dimensional heat equation in there. Okay, well, taking that number and then, of course, dividing it by 300,000 and dividing that by 4.186, I get 1,195 cubic meters in a day, which actually seems like a pretty big number to me. So let me check the answer. Oh, and they got a very different answer. Let's see. What did
Why
we
did
do?
they divide by 9,300 kilocals per meters cubed?
Hang on. Okay. Let's see. Let me go all the way back to the area. Did we? Okay, so we agree with the area 304. Oh, now. Okay, so in the conductivity, they do kilowatts, which then give a rate of. So I got 17,000 watts, and they got 17.4 kilowatts. Okay, so check that. That looks good.
I know that in here it says that the energy of the gas per cubic meter for 9,300, or 9,300 kilocalories.
Oh, did I write
Yeah.
this down wrong?
Yeah, I think that might have been it.
Ah, okay. Let me come back to the problem. Yeah, that little space in there. I just saw. Well, doesn't matter what I saw, but I didn't see that 9. See how there's a 9 and then a space and then 300 kilocals. I did just in my mind as I scanned it real quick. I just grabbed that 300 kilocals. That's why I did that. All right, so let me come back over to here. And get the right number. So it's 9,300 kilocalories. All right, so I'm going to try this again. Let's take that number and then divide it by 9,300,000. Divide it by 4.186. And it looks like I got 38.6. And the units would still be cubic meter per day. And what did they say? Yeah, 38 points. Yeah. All right. So just didn't read that 9 and the conversion factor. Nice.
That one does match up with the solutions, right?
Yeah. And so I did. Yeah. I just flipped over the solution. So it matched. Good.
Awesome. Thank you. When is the next session again of today?
Oh, I believe we break at 2. So let me look at my calendar, my chart here. Yeah, 2. Yeah, we break at 2 and then come back at 3. So 3 to 4:30. Yeah.
Cool. Awesome. I'm going to head out, but I'll see you then.
Okay. All right.
There's no questions. I have a quick question about 20 number 1.
Okay.
So I did the first part fine. The just mass times hold on, I'm scrolling up. The mass times gravity times height, that makes sense.
Okay.
So I guess I don't understand the next step of that.
Well, okay. So I'm going to draw your attention back to Physics 121 because in 121 you learned that the potential energy is mg, and sometimes we write that as an h, sometimes we write it as a y. The release of energy would be the change in y. So sometimes we do that. So I don't know whichever one you want to feel more comfortable with here, but the problem talks about this waterfall, and this was a very interesting historical step for Joule. Is he reasoned that because of conservation of energy, the water going off of a waterfall would then lose this much potential energy, so mgh, and it would then go to the heat, which if we're talking about water, it's mc delta T. So if you were to kind of look at the top of a waterfall, and let's say you grabbed, just I'll make a number up, you're kind of focusing your attention on 1 kilogram of water. As it goes over the edge, it would, of course, lose the potential energy and really become kinetic energy. Then it would hit the rocks down below and become heat energy. And so this much potential energy then gets converted into heat energy. And he was trying to kind of prove this. Nobody at his time knew what heat was, and he was trying to prove that it was heat energy, and that heat was just another form of energy. And so that potential energy could be converted into kinetic, and kinetic can be converted into heat. So that was kind of his logic. So he goes to this waterfall and he says, all right, so that means the bottom of a waterfall should be warmer than the top. Now, he wasn't really sure how much, so he put a thermometer in there and found no temperature difference and was a little bummed that his theory wasn't working out. But this problem is asking you to kind of go through why. And first of all, notice that the M is on both sides of the equation. So if you're looking at 1 kilogram or 2 kilograms or 3 kilograms, it doesn't really matter. The more mass you look at, the more energy it has, but then also that has to warm up more water. So whether this is a little bit of mass or a lot of mass, it's irrelevant on how big the waterfall is. And I don't mean height-wise. Height is relevant. And he realized that. So he goes, oh, I'm going to go to a tall waterfall. This is a pretty tall one. This is 50 meters. So if we put in these numbers, G is 9.8. The height is 50 meters. The specific heat of water is 4.186 joules to warm up 1 gram. And I should probably do kilograms. Let me be careful with my units here. This is meters per second squared. This is meters. Let me make an adjustment here. Let me think about it for a second. I know that specific heat of water is 4.186 joules per gram per each degree. If I multiply the top by 1,000, I'll move the decimal to there, but to match it, I got to multiply the bottom by 1,000. So there's a kilo. Okay. And then delta T. And then a joule is a kilogram meters squared over seconds squared. So kilogram, we cancel with that kilogram. Meters squared on the left would cancel with meters squared on the right. Also per second squared on the left would cancel with per second squared on the right. So we're going to be left with just a delta T. And it's a pretty small number here. It's 9.8 times 50, then divided by 4,186. And it's a little more than 1/10 of a degree. And I think the history and the story here, it goes that Joule thermometer was not that accurate. You can only measure something like 1/2 degree. And so this change, even if the change existed, it was so small that he didn't notice it, and it kind of threw him back a little bit. Later on, he would continue on his theory of conservation of energy and heat energy and the first law of thermodynamics. But at first, it threw him back. He's just like, oh man, it should have been warmer, and it wasn't. But number one, his thermometer couldn't have measured it, and number two, it probably actually wasn't really warmer, because what's ignored here, and this problem talks about it, is as the water falls, it does have this mist, this evaporational effect. And so there's a cooling effect. So that cooling effect, a lot of times, can be more than the actual warming effect due to the falling of water and the energy. So many waterfalls are actually cooler down at the bottom because of the evaporational. Kind of reminds me of those misters, if you've ever been to a hot place, Palm Springs or something in Las Vegas. They'll put the strip with these misters. They shoot these little fine mist, and that evaporating cooling works really, really well. And waterfalls naturally do that. So the bottom of the waterfall, despite this beautiful idea behind Joule, just doesn't work.
Okay. Cool. Thank you. I'll see you at 3.
All right. Yeah, we'll take a break and see you at 3.
Bye.
Bye.